orbitals like Kojima or Shika and Soma on the one hand, and a PhD thesis by Tsao. On the other hand, I think none of these documents is really complete in any way, and there are various, well, errors and omissions throughout them. So I think it's been a long time. It's been needed to have an actual proof of the theorem. So I want to advertise a little bit the structure of the theorem as, again, the role that the cyclic fiber, this sort of collapsing operation, plays in it. Now, what is the theorem? The theorem is a geometrization conjecture for orbifolds. So it's a geometrization theorem for orbifolds, or in particular called irreducible orbifolds. So, again, an orbifold is just, a three-dimensional orbifold is just something locally modeled on R3 divided out by finite group. Now, there are two sort of classes of finite groups. These will be a fixed point, so some kind of subgroup of SO3 for assuming some orientability. There's either a cyclic group where you'll have an axis, it's just really a three-dimensional version of the two-dimensional rotation, or there are the groups that are sort of modeled on the Platonic solids. Now, I'm going to assume that we're in the situation where the local groups are all of the cyclic type. What that means is that the singular locus, just as before the two-dimensional case, the singular loci are all just points. In this case, the singular locus for a general three-dimensional orbifold orientable will either be a length or more generally a graph. And so I'm going to be restricting to the graph, to the length case. In general, the Platonic solids, you have a graph where you have different bits of one-dimensional singular locus coming into a point. So the general orbifold theorem does deal with that case. We haven't worked out the proof in that situation. But I think the main case is the one I'll actually discuss. I'm going to further discuss only the case where, so if you remember the original geometrization conjecture theorem, even in the Haken case, said that you could decompose along tori into, if it was already irreducible, into geometric pieces. Okay, so I'm going to assume, furthermore, that there is no decomposition along sort of two-dimensional analogs of tori, or orbifold versions of tori. So one way to describe that is to say that there are no decompositions along spherical or Euclidean suborbifolds. Now, being sort of precise, what I mean by this is there's no two-dimensional. So remember, irreducible meant that any embedded two-sphere bound with a three-ball. So in particular, if we see a regular plain old two-sphere like this, we want it to bound a three-ball. So that's okay, but you don't want it to bound something more complicated. So the sort of orbifold versions of this is you could have a two-sphere with two singular cone points. So locally, this is just two-dimensional space divided by cyclic group of order P, and this one Q. So we don't allow it where these P and Q are different. We don't allow this case either where there's just a singular point. We're also ruling out this case here where there are 3 points and the sum of the 1 over P, 1 over Q, 1 over R is greater than 1. So this may look familiar. What this is geometrically is it's two spherical triangles glued together. And this inequality here implies that there's actually a triangle with angles pi over P, pi over Q, pi over R. Okay, so you can find two of these. So these are all ruled out. There is a kind of natural local structure just along near the singular locus, which is in general going to be just a piece of length where you divide it out by rotation of order P. So this is a sort of natural model of a ball around such a point. So this is certainly okay too. So these are the things that are all right. These kinds of suborbifolds are ruled out. Those are the sort of spherical-looking objects. The torus analogs, again, there are no non-trivial embedded tori. So that means there's no tori whose fundamental groups inject. We also don't rule out the Euclidean analog of these double triangle groups. On the other hand, certainly a singular locus for the length will locally, this will be a generic picture. This would be the picture around the singular locus is just a solid torus around the simple closed curve, so that's okay. And then there's another structure here, which is a ball. So it's a sphere. It has 4 singular points, all of which have order 2. So you can think of it sometimes described as a pillow, or it's rather a pillowcase, and you think of it as having right angles there, so it would just be like a pillowcase. It would be like a doubled rectangle. And then this picture, on the other hand, it bounds a sort of pillow, I guess. This is, if you take a 2-fold branch cover of this over the singular locus, you'll get a solid torus. So this is a sort of orbifold version of saying that every torus bounds a solid torus. So this is okay. You're not allowed to have that picture of a 2, 2, 2, 2 that doesn't bound, that doesn't fill in this way. Okay, so that's the kind of orbifold version of atoroidal and irreducible. Okay, so then the theorem is that these orbifolds have geometric structures. So if you take say, a closed, stick to that case, a closed 3-dimensional, orientable 3-dimensional orbifold, it's important that it have a non-empty singular locus. Otherwise, this would be kind of strictly stronger than the geometrization conjecture. So it would be an important first step to use the fact that the singular locus is non-empty. We want to assume that there are none of those pictures, that it's irreducible and atoroidal. Then it actually has a geometric structure. Now, a more general theorem, even in the case where you only allow linked singularities, is that it should decompose along tori and orbifold versions of tori, so along Euclidean orbifolds into geometric pieces. And that basically would boil down to proving a relative version of this theorem. I don't think that version of the theorem is much harder than the version that I've written up here. I haven't worked out all the details of that. So Boileau and Forti have also proved essentially the same theorem with a bit of an extra hypothesis that the orbifold Q is good. What good means, I guess this was back in the days when it was okay to make value judgments. Good means that there's a notion of universal cover of an orbifold, that's actually a manifold. Now locally we know that you can sort of, everything just looks like Rn divided out by a finite group, so locally there's a sort of finite cover, in fact that's a manifold. But in general you needn't find a universal cover that's actually a manifold. In fact, here's if you want to think about it, the fundamental group of this object here is generated by 2 elements, one going around here and one going around here, one of order P and one of order Q. But the fact that they're the same element means that they're equal. So if P and Q are relatively prime, then this actually is a simply connected orbifold, but it obviously, so it actually is its universal cover. So that's a simple example of an orbifold that's bad, 2-dimensional orbifold. Now, in fact, the theorem here implies that ruling out these kind of bad suborbifolds, 2-dimensional suborbifolds, that Q actually is good. So one of the corollaries of the theorem here is that Q actually does have a manifold cover. So in some sense, they're not dealing with any fewer examples, but they need to make this extra assumption at the beginning. So how does the proof go? So I just want to sort of first go through the kind of basic steps, the outline, and then kind of zero in a little bit on this collapsing part. So we'll see Seifert fiber structures appearing again. Actually, they appear already in step 1 in sort of the same way they did in the geometrization conjecture or theorem of Thurston, the manifold version of it, and that there's this kind of dichotomy. So let's take the orbifold, this 3-dimensional orbifold. It's irreducible, and we're assuming there's a non-trivial singular locus. So there's some link sitting in there where we have these kind of local models. I've actually already drawn the picture here of the local model. You want to think of it as kind of just a wedge, sort of the 2-dimensional rotational model across a circle. So there'll be some non-trivial length in this orbifold. We throw that away, or throw away a tubular neighborhood of it. Now we have a manifold with torus boundary. Since it has non-trivial boundary, it's Haken, and so Thurston's geometrization theorem applies. It has a geometric structure. The manifold that now, when we take out the singular locus, it's a manifold. It will also be irreducible and atoroidal, and because it has non-trivial boundary, it's Haken, so it's geometric. So if we remove the singular locus, we can get a geometric structure. Now there's sort of two cases, as I said, where you have some torus boundary. Either it's Seifert fibered, or the interior has a hyperbolic structure. So if it's Seifert fibered, what you find out, you want to take the Seifert fibration, which exists in the complement of the singular locus, and extend it to a Seifert fibration of the orbifold. In particular, you want to include it include the singular loci as elements in the fibers. Well, the only instruction to that would be if you've got geometrically, topologically a solid torus there, the only problem that could happen would be that the fibers actually go around the meridian in that direction. If that happened, there's an argument that shows you to not be in the irreducible case. So you can show that in this situation, the Seifert fibration actually extends to include the singular fibers, and so you have a Seifert fiber orbifold and a fairly straightforward generalization of the Seifert fiber structure of a manifold. So the singular loci are just fibers. And it's quite easy to get those geometric structures. So the other situation is where there's a hyperbolic structure on the complement. So now what are we going to do with that? Right? We need to think about what that structure gives us and where it is that we want to go. So what is geometrically the structure that we want? So I want to now think about, suppose you're trying to find a hyperbolic structure on this orbifold. Well, it'd be a hyperbolic metric in the complement of the singular locus, and then what's the metric structure near the singular locus? Well, it's going to consist of a geodesic and hyperbolic space together with a rotation of by angle 2 pi over p, where I attach that side to that side. So this, again, it's the same topological picture we've been looking at. Topologically, it's just a solid torus with a singular curve drawn in it and a core. But there's sort of more information there, which we've denoted in the orbifold language by the p there. But metrically, if this were a hyperbolic structure, it would also tell me sort of metrically what's going on around there. So if you think of a disk transverse to the singular locus, there's no longer angle 2 pi there. It's not going to be a smooth point. Right? Instead, there's an angle of 2 pi over p. So as a metric object, you can think of this as a hyperbolic metric on the complement of the singular locus, which is incomplete, and when you complete it, you get this sort of singular metric, which has this property that concentrated along the singular locus, you have angle 2 pi over p. Now, the idea of trying to get to this picture, what are we given? We're starting with a complete hyperbolic structure on the complement of this. So let's think about the picture we want. If you just think about cross-sections, here, is we want to have this just identified with 2 pi over p angle. And what do we have? If we have a hyperbolic structure with finite volume, then this sort of core curve here is off at infinity. If you took a cross-section there, you would get, in fact, a cusp. You want to think of that as a hyperbolic triangle where the angle is 0. So you want to think of starting with a situation where this has angle 0 for the cross-section, going across here. You want to push it, you want to change things so it has angle 2 pi over p. Now, the one problem with sort of theory of orbifolds is that there's this idea that you need to have things modeled on a cyclic group. And the cyclic groups just come in one-to-one correspondence with the integers. And the integers are discrete, so it's sort of hard to interpolate between different orbifolds. You can't sort of find a continuous path between 2 and 3. Or in particular, as we're interested in here, sort of 0 which is like infinity, and all the other integers. So what we need is a kind of geometric object which will help us interpolate between these two structures. And again, the basic idea is to interpolate between an angle of 0 here and an angle of 2 pi over p. So you want to think of the same metric structure. You have a hyperbolic metric on the complement of the singular locus. And I want to perturb it. I want to change it through hyperbolic metrics, again on the complement of the singular locus. That's what M is here. M is the complement of the singular locus. I want to vary the hyperbolic structure starting with this complete finite volume structure and get to this model structure, where again we have so that always sounds funny to people that are familiar with Mostow rigidity, where you tend to think of hyperbolic structures on 3 manifolds as rigid. And if you're talking about finite volume complete structures, they are rigid. So here we're going to be varying the hyperbolic metric on this open manifold through incomplete metrics. Okay, if you remove that singular locus, and if you think about the model that we actually want, in the limit, if you remove the singular locus, it's a nice smooth metric, but that singular locus is actually a finite distance. So you want to think of, you're going to build a one-parameter family of hyperbolic metrics in the complement of the singular locus, whose completion is a singular metric where we fill in this singular locus with a length's worth of singularity, where the angle at time 0 will be angle 0, and then at time 1 will be the desired angle. Okay. So this is a goal here, is to try and vary the metric on M until you get starting at angle 0 and try to perturb it so you have this kind of incomplete structure that has this nice completion starting at angle 0 and getting to angle 2 pi over p. And we just go ahead and try to parameterize this. We try to find a one-parameter family of these metrics and just parameterize it by the do it linearly, so at time 0 it's the complete structure, and at time 1 you're at your desired structure. Now it's not immediately obvious that you can even get started, that you can perturb the structure at all, but that you can increase these angles at all. This turns out actually not to be that difficult. There's a nice argument. It involves the dimension count on the variety, the representation variety of the fundamental group of M, and the fact that at the complete structure you have rigidity. So you prove that there's dimension. Well, think of the case of a single piece of singular locus. You prove that the dimension of the variety is non-trivial. In fact, it turns out to be exactly one-dimensional. So there's some deformations, on the other hand, by Mostow rigidity. You can't deform through complete structures, so you have to go somewhere, and a little more argument shows you can actually increase the cone angle here. Now, you don't actually need this in the argument of the theorem, but I find it sort of psychologically more useful to think about the fact that as you're increasing these angles, there's actually locally just a unique hyperbolic cone manifold structure. That's what we call these structures that have this kind of singular metric, or the incomplete metrics that complete in this way. So there's actually a nice path, or well-defined, that's just parameterized by the sequence of angles. Okay? So locally we can increase the cone angles. The question is, can we get to our desired set of angles? Right? So what can happen? Right? Either we get there or we don't. Well, what can possibly get in the way of our getting there? Okay. So let's just sort of organize the question about what happens. Let's let capital T, so for a while you'll just have a hyperbolic cone manifold, so we have a hyperbolic structure. Now let's let capital T be the largest value, so that this q sub t, that's just going to be this incomplete structure at time t, is still hyperbolic. If we can get to t, capital T equals 1, then we're done. We'll have a hyperbolic structure on this orbifold. Okay, so that's the goal, at least if we want a hyperbolic structure. Well, the first observation is, so we have a sequence of metric spaces. Okay, and they're in general fairly nice in the sense that they're hyperbolic metrics. On the other hand, they're incomplete metrics, so there's a certain amount complication involved with that. But it makes sense to talk about the injectivity radius and other things that one normally associates with a Riemannian manifold. It just happens to be an incomplete one. So again, the injectivity radius is, if you think of at a point, is you think of taking the exponential map. It's sort of the radius of the largest embedded ball. So it's the point at which you start coming back and hitting yourself in the exponential map. Okay, so it's the radius of the largest embedded ball. If the injectivity radius throughout my one-parameter family stays bounded from below, so nothing is sort of getting small, so you have nice little model pieces of hyperbolic space, then it's fairly easy to see that in the limit you end up with a hyperbolic cone manifold. Well, since capital at time capital T, since capital T was supposed to be the maximal value between 0 and 1, it means that capital T is 1, and we've succeeded. We've gotten to the hyperbolic orbifold. So the real issue is what happens when the injectivity radius goes to 0. Okay? That's where all of the action happens. Now the injectivity radius can go to 0 in a lot of different ways, and the bulk of the argument, of the sort of structure of the proof, is to try to analyze how the injectivity radius can go to 0. And try to rule out certain things, in particular when it goes to 0 in certain ways, to try and derive topological conclusions. In particular, the usual topological conclusion you get if it degenerates in certain ways is you get an incompressible torus, or an orbifold version of an incompressible torus. And that's been ruled out in the original hypothesis. We still have the theorem. Right, so remember here that the three manifold is assumed to be atoroidal. There we go. So one of the main steps is to sort of derive incompressible tori or incompressible Euclidean orbifolds when things degenerate a certain way. Okay, but I'm not going to actually talk about the sort of logic of the argument. I want to talk rather about sort of, so a lot of the argument is just a matter of proving that certain things don't happen. But so what I want to actually do is tell you what does happen. So Dennis's approach to positivity, positive statements. Okay, so one way that the injectivity radius can go to 0 is that the whole manifold can kind of collapse to a point. The entire diameter of the manifold can go to 0. So then your sort of limit in some geometric topology is just a point, and there's not too much you can do with a point. So we're going to rescale if the diameter gets less than, say, 1. Let's just go ahead and rescale it so that the diameter is 1. Okay? So now we'll have a sequence of manifolds whose diameter is greater than or equal to 1. We can talk about something that will be some kind of limiting object. Now what happens to the curvature when you scale by lambda t? Well, the curvature, which was curvature minus 1, becomes minus 1 over lambda squared. So it's still negative, but it's going towards 0. So now there are two sort of cases. Either the injectivity radius of the scale thing stays bigger than epsilon for all t, or it doesn't. So let's sort of quickly go through the first case. So again, now we're in a situation where, again, the injectivity radius is bounded below. Well, there nothing is collapsing. You have fairly good models. The only thing that could be going on, well, so either that lambda t stayed finite, we didn't have to rescale off to infinity, in which case we're really in the case we did a minute ago over there, where our limit is a hyperbolic orbifold. Or we had to scale off to infinity as time t went increased to capital T. In that case, the curvature will go to 0, and the limit will be a Euclidean cone manifold. Okay, and again, there are two cases. Either we're at our time capital T, our time capital T is equal to 1, so we've gotten to our desired angles, in which case Q has a Euclidean structure. Q here is the orbifold, so we've succeeded in putting a Euclidean structure, or we didn't get to the desired angles yet. And now you have to make use some rather deep theory of Hamilton on three-dimensional manifolds with positive Ricci curvature to ultimately prove that if you haven't reached your desired angle, you can actually give a spherical structure to the underlying orbifold. Okay, so I'm not going to talk in any detail about that. That's sort of another whole little story. Although once you have Hamilton's theorem, the argument isn't that hard.
Did Pearson have Hamilton's theorem?
Yes. Yeah, it was sort of amazing how the timing. I think there are other arguments you could try to use using homological arguments, but I've never seen it work for sure. It's more delicate. Okay, the other case is that the injectivity radius is going to 0. Okay, even if my scale thing. Now the conclusion here is that we actually are at our desired time, so we're at our orbifold angles, and furthermore that we actually have some kind of Seifert fiber orbifold. Now, let me just, before I say anything more about that, so this is, we'll start to see Seifert fiber orbifolds coming in here. But let me say a couple more things about what you can actually see in the proof here before I leave this slide. So, this sort of process of increasing the cone angle and then seeing what happens gives you more information really than just that you get the geometric structures at the end. You can actually say a bit more. You actually never degenerate at all until at least one of the cone angles becomes greater than or equal to pi over 3. So at least one of those cone angles has to be greater than pi over 3. So this tells you ahead of time that if none of your angles on your orbifold were that large, they all had high p's in the cyclic group, then in fact you're going to have a hyperbolic structure on that orbifold. So this is an observation that Zhao made in his thesis. Also, the case 1b, the Euclidean case, and the spherical cases are all sort of easily classified. So, the conclusion here actually, except in 1a, we really have a sort of complete knowledge in case 1 at least of what we've got. Now, as we'll see in the second case, where we actually have the injectivity radius going to 0, at least one of the cone angles has to be equal to pi. So this is, again, in other words, the cyclic group is of order 2, which is the smallest order that you can have. So you only have this collapsing case when at least one of the numbers on the link is a 2. In fact, we'll give a fairly complete, in this atoroidal situation, description of what they have to look like. But that's a kind of general effect. Okay, so in case 2, not only is the injectivity radius going to 0, so that just means at some point you're getting a very, very short geodesic going through that point, but actually the injectivity radius is getting small everywhere, all across the manifold. And in some sense, this is the biggest step throughout this, is to show that if in these situations the injectivity radius goes to 0, it has to do so uniformly. So this is again, this is a phenomenon that's been studied in a lot of detail by a number of people that a lot of them around here. The idea of collapsing manifolds. So the whole manifold is getting thin. On the other hand, remember we scaled it so the diameter is not going to 0, it's not shrinking to a point. So there's some manifold there. So you want to think it's really collapsing down to some two-dimensional object or to a one-dimensional object. Okay. So let me just say a little bit about the sort of manifold theory of collapsing manifolds. So if you remember the picture of the Seifert fiber spaces that we had kind of at the beginning, have this kind of local structure of these fibers here over this manifold. It's fairly easy to convince yourself that you could find a one-parameter family of metrics here that just shrinks the lengths of the fibers, so squashes it down to a metric, but without making the whole diameter go to 0. Okay, so you can just sort of squash it down. Even though it's not a product, it's sort of locally enough of a product that you can define a metric that just sort of squashes it down flat. So again, it's fairly easy to see that there are such metrics on these Seifert fiber spaces. Well, there's a kind of converse to this phenomenon that says that if you're getting a manifold that's flattening out, particularly the injectivity radius is going to 0 everywhere, well, rather than, so the sort of the theory of Cheeger and Gromov and Fukaya, rather than talking about the diameter, I mean, one way that you could make the injectivity radius go to 0 everywhere is just to take the whole manifold and scale it to a point. But then the metric would blow up, the curvature would blow up. So the sort of analytic way of dealing with this is just to put a bound on the absolute value of the curvature, say an L infinity bound. So in that situation, you have a bound on the curvature, and the injectivity radius is going to 0. This is called a manifold collapse. As I said, in the Riemannian geometry world, this was studied in detail by Cheeger and Gromov and Fukaya, and Thurston actually had introduced these ideas in the context of hyperbolic geometry. So, again, these are ideas that were in the air around the time, somewhat before the orbifold theorem was originally outlined. Well, so the conclusion, the general conclusion that Cheeger and Gromov give is that M has what they call an F structure. And the F structure is supposed to remind you of foliations, is their name. And it's not quite a foliation, but it's sort of a mixed type foliation. You get a kind of foliation of bits where the leaves are circles or tori, and they kind of mix together, so that if you have a bunch of circles coming over near the torus leaf, they kind of wind around the torus in a nice way. So another way of describing this is that you have sort of locally, well, in n dimensions, you'll have locally some kind of torus action. And so you get a kind of generalized picture of a Seifert fiber space, but where the dimension of the leaves, of the dimensions of the orbits, can change from point to point. So it's a kind of generalized notion of these Seifert fiber structure. And in fact, in dimension 3, you can prove that what an F structure ends up meaning is that it's a Seifert fiber structure, perhaps with some torus boundary and then a bunch of those glued together. So it's what's sometimes called a graph manifold. Now, where does this foliation come from? That's sort of one of the things I want to sort of leave you with, or to understand. Why do you get a foliation when you see a collapse? Well, let's imagine, in fact, let's go over here where we have a manifold that collapsed. Imagine collapsing, the metric is kind of collapsing like this, okay, but it's not collapsing horizontally. Let's go back and rescale some more so that the injectivity radius is not going to 0. Then whether or not that lambda sub t went to infinity or not before, I'm definitely rescaling off to infinity here because it's collapsing. In the limit, I'm going to see a piece of a Euclidean manifold. Right? And that's true even in the variable curvature things. You're going to be rescaling, so it's going to look closer and closer like pieces of a Euclidean manifold. So in the limit, you kind of get a piece locally all around them at every point of the manifold, because every point the injectivity radius is going to 0, you get a piece of a Euclidean manifold. But the Euclidean manifold will, of course, in general not be, in fact, in this context that we're dealing with where the diameter is not going to 0, will never be compact. So, I mean, if you think of just this local picture, if you rescale, you're just going to end up, if you rescale so the injectivity radius going up and down with 1, you're just going to end up with the interior of a solid torus, or an S1 cross R2. So that's the general picture, and so the analysis here is that locally, these Euclidean manifolds look like essentially some compact lower dimensional Euclidean manifold. Well, a bundle over that, or say cross, again by taking some finite cover, you can get sort of a local structure of something like a torus of some dimension cross RK. But as I said, you get what you really end up with is some kind of group action, sort of torus group action, where the dimensions of orbits can vary from point to point. So the main reason you end up with this sort of foliation, this F structure, is because Euclidean manifolds have them. Right? Euclidean manifolds, all, even the non-compact ones, basically look like tori. And the leaves of this F structure correspond to those tori. Now, that's fine, you get a sort of local structure, but that doesn't do you much good unless they somehow glue together. And then the key fact is that, well, where did these the compact part come from? Well, where did it come from over here? It came from the short geodesic, from the short curve. And the fact that you have sort of injectivity radius going to 0 everywhere means that you have short directions everywhere. And so when you locally you get this sort of piece of Euclidean manifold, if you look at an overlap, well, where did the compact pieces come from? They came from short curves, so there has to be some sort of agreement. So that's roughly how the Cheeger-Gromov argument goes. You locally get these pieces of Euclidean manifolds, and because the compact part, because the Euclidean manifolds come from a geometric construction, they kind of fit together nicely. Now in our situation, we don't quite have a nice Euclidean structure, and there's actually a similar theory that was developed, well, which mirrors to a certain extent this Euclidean structure. Manifolds are of most interest in the non-compact case that have non-negative, I guess, Ricci curvature. And there's the structure theorem here of Cheeger and Gromov that says that basically there's some compact piece, which they call the soul, right? And that the three manifold, or the N manifold, will just look like will be diffeomorphic to the normal bundle of this sort of convex submanifold. So it'll look like a convex submanifold across some Euclidean space. Okay? So even if you have some positive curvature, positive Ricci curvature, you still get much of the same kind of product structure that we have here. Okay, so this is a kind of key, this idea of having a soul. So I guess, before we had guts to hyperbolic manifolds, and when they degenerate, all you're left with is the soul. So this was, let me just quickly talk about, it's not quite a product. Let me just show you a two-dimensional example of a soul. So if you just take out, I meant to put 2's on here. So here's an orbifold picture with a soul. So it's just a disk with 2 points of rotation of order 2. It's easier to think of it as a cylinder where you kind of rotated by order 2, so that closes up half of it. So if I had a complete infinite cylinder here and rotated around an axis, so it's just the surface, then I'd end up with a half cylinder that's kind of closed off here. Okay? I'd still have just these 2 singular points, and the soul is this green arc, the geodesic that joins those. And you can see that the structure here isn't quite just a product, because it's not just a soul across R, but there's a sort of order 2 fold as you're going through here. So, but you still have essentially this kind of product structure. So this is the kind of structure that one wants for a Euclidean cone manifold. So what one needs to replace this collapsing theory in the situation of sort of Gromov-Cheeger collapsing theory is some kind of structure of non-compact Euclidean cone manifolds where the cone angle is less than or equal to 2 pi. And so what we proved is a soul theorem for these kinds of cone manifolds. Okay, so there's a sort of compact bit, which will again be sort of cone manifold, but of a lower dimension, and things will essentially be that product structure of that compact piece across an Rn. As I say, it's not exactly that. You can have these kind of folds, like I just showed you a picture of. But after a sort of finite cover, you can end up with that. Well, so that reduces the dimension. It simplifies things. Now we're talking about compact cone manifolds of dimension 2. Again, where the cone angles are less than or equal to pi. Well, those are fairly easy to list. In particular, you can just take 2 triangles where the...
follows directly from solid view.
Excuse me?
It follows directly from classical solid view. Just by approximating.
Right, well, you need a bit, we actually want a bit more information here, I think, but I mean, it's not a big, I mean, it's just a matter of doing it. It's the same technique. So, well, yeah, anyway. For example, a two-dimensional Euclidean cone manifold could be gotten by taking two Euclidean triangles and gluing them together. So that would be like a sphere with 3 points, and then we'd have it cross R. But this is ruled out because, remember, we didn't allow these pictures with 3 points there where things added up to, well, the way I had it in before, so that the denominators added up to 1. That's sort of the same thing here. Either it adds up to 1 or it's greater than 1, depending on whether we're at our final angle or not. Okay, so these are sort of ruled out. Most of the pictures are ruled out by the toroidal and irreducible conditions. All right, so remember I said that we're going to see Seifert fiber spaces again, and that was certainly suggested by this S structure situation. But remember, we threw away, we already dealt with the Seifert fiber case. So why is it kind of reappearing again? But remember, the original version of the Seifert fiber spaces, the singular locus were among the fibers. So the Seifert fiber structures we'll see will actually be a slightly different kind of Seifert fiber structure, where the fibers are no longer, the singular locus is no longer part of the fibration. Okay? And the model to think of is as follows. Okay, so what just locally, even along near a regular fiber, what does the picture look like? You just have, for a regular Seifert fibration, you just have a solid torus. This is attached to that with no twist. Okay. And we just take the standard product foliation. Now I want to take, okay, but again, remember that's identified to that. Now let's take an order 2 rotation. We just flip this around. This disk here is folded over. It's taken to itself, so that's attached to that. On the other hand, the bottom is taken to the top here and vice versa, so you have a sort of fundamental domain of this piece. But remember, this is a solid torus, so that's attached to that. And the effect of that is the top piece also gets folded over itself. So you really want to think, even though it just rotated there, there's also a fold there, which is equivalent to a fold there. Okay, so the topological picture you end up with by taking sort of half of the original solid torus, which again, and just folding over the top and the bottom. So that's just this picture, but now I fold that part to that part and that part to that part. Topologically, I get a ball, but I have this singular locus going through with an order 2 rotation, singular locus there. So topologically, it just looks like the picture I showed you the solo of a minute ago, cross I. So this is the kind of local structure that one gets. And this is a sort of only allowable local structure. Remember, my original, or may not, but the original allowable case when we were doing the torus decomposition situation, this was the one allowable picture, which I said then was solid torus divided out by an order 2 rotation. So you get the original where the foliation here is taken to itself, but the fibers that go through the rotation axis get folded over one to themselves. All the rest are taken off themselves, and one in the front, one in the back. So they just close up, they just remain circle fibers. Okay, but then we have these kind of singular fibers, which are just arcs, right? So they're arcs with tubes on them. So this is sort of, you think of this as a one-dimensional orbifold, where it's just a circle divided out by an order 2 rotation. Okay? So this is the idea of a Seifert fiber orbifold foliation, Seifert fibration. Okay, so this is an orbifold version of a Seifert fibration, where the fibers are one-dimensional suborbifolds, right? So they're either circles or they're intervals. Okay, and this is the sort of local picture that you'll get. On the other hand, you can, even though topologically that's the picture you get, geometrically you can get a more complicated picture, just as in the case of the Seifert fibration. You can actually have the two sort of rotation axes coming down at some kind of rational angle to themselves. And then when you take a rotation order 2 and order 2 there, you'll actually generate, sort of in the limit, a kind of dihedral group. And here you get a more complicated sort of singular fibration. You not only have the singular fiber, you do it here, going from there to there, the regular fibers, instead of going around twice, as they did here, will go around 2p times, where p is the rotation you have there. So in particular, you go up to the top here, but that's attached to there, which goes attached to there, and so on. You go around that. You'll also have some fibers that run along the singular axis that are twice as long, generally p times as long as the thing in the middle. They would go up here, and then flip over, and then go down. So this is the kind of local structure that you get for the sort of Seifert fibration. Okay? So this is the kind of, and again, just as in the sort of S structures, you can piece these things together, but they can be glued together in a fairly complicated way. Okay, so let me show you the structure theory. So this is the sort of new way that the Seifert fibrations reappear sort of at the end in this collapsing manifold. So it's a kind of orbifold version of the S structure. And I think it's a sort of interesting kind of new structure. So here's the kind of example that you can end up with. Be familiar to at least the knot theorists. This is called a pretzel knot. You've got these twists. This picture here corresponds to this kind of picture locally glued together to this kind of regular fiber picture. When you do that, the singular locus gets all twisted together, and you end up with some picture like this. You get some finite number of local structures like this that are what are called rational tangles, and they're kind of glued together. Now, in the atoroidal case, so you can think of, if you take a Seifert fibration, you should have a base space. Again, we have a base orbifold. In this case, it'll be a 3-3-5 triangle with sort of mirrored faces here. Again, where are the regular fibers? Just quickly draw that in. The circles go around, not there. And then we have the singular fibers, the regular singular fibers, the regular intervals fibers in there. And there's a sort of really singular one there corresponding to the singular the thing in the center over there in the lower picture. Now the atoroidal condition that I put in here puts a lot of restrictions on what you can have. Remember, the general Seifert fiber space in the non-singular case almost always had tori in it, except for the 3 times punctured spheres. So again, we get a fairly simple classification in the atoroidal case. It basically has to look like this, or possibly fewer singularities, fewer not the singular fibers of that sort. So that's the sort of final build. Thank you.
Any questions?
So you start out with the assumption that the faults are atoroidal. You have a sort of a relative version where you would have like cusp or a cusp.
There is a relative version, we haven't proved it yet. I think this is really the main step, and we just haven't worked out all of it, so I won't write that one down yet. It's also harder to say. But yeah, the sort of 2 remaining steps, the theorem that I originally wrote down, the atoroidal version, is just a very special case. And the 2 next steps, one is to do the torus decomposition, and the other is to allow the grass singularities. I don't think either of those would be much different.